Welcome back to CS479 machine learning for 3D data. So we are discussing the basic ideas about the diffusion D models, and let's briefly recap the things that we discussed the last time. So basically, we are discussing the idea of the DDPM, which was basically having the forward and the reverse the processes in a way that we can map the given the data distribution into some kind of a target distribution or the priority distribution, which is typically the unique Gaussian. And also the reverse process is basically doing the reverse mapping from the unique Gaussian to the data distribution in a way that we can basically sample lots of the data from the learned the data distribution. And both the forward and the reverse processes are basically modeled as basically the Markov chain. Basically, the meaning of the Markov chain is that each of the variable at the time step t only depends on the variable from the previous time step, not the other kind of things. So these are basically things. We are basically stacking this kind of the multiple the transition the distribution in a way that we can map basically the data point sample from the data distribution to the target distribution. So we are basically mapping the variable from the sample from the data distribution to the basically x capital T at the end of the all the transition to the target distribution. So don't get confused with all the kind of the notations about the time. So we are basically starting from the time zero to basically the capital T in a way that we are basically mapping from the data distribution to the target distribution, which is the forward process. And the other way around, basically mapping from the prior distribution to the data distribution was basically the reverse process. So literally basically going into the reverse way in the time domain, the capital T to the time zero. So this was basically the forward process, and we basically modeled each of the single transition as kind of the Gaussian distribution like this. So these are basically all some kind of the usual parameters that we can choose. So when you also define the forward process like this, the reverse process is also defined as kind of the another the Markov chain in a way that we're also having starting from the data distribution and going back to the data distribution with this kind of the Gaussian the transition. So it starts from the unique Gaussian, and the goal is basically like given the kind of fixed the forward process, basically how we basically estimate the parameters for the transition for the reverse process was kind of the goal in the neural net training. So that's basically what we are going to do. So we are basically going to basically predict some kind of parameters for the reverse transition and some kind of the properties that are desired to basically make this kind of process to be working is that we need to set the parameters better in a way that they should be basically small enough in terms of the reverse transition can be basically approximated as kind of the Gaussian transition. But the thing is that if we basically make this kind of data to be small, we also need to have lots of this step. So as when the t is basically is going to the infinity, we can say that the forward process can basically converge to basically the unique Gaussian. So that's basically the properties that we need to basically satisfy in terms of designing the DDPM process. So all the beta t should be basically small, while the t should be basically basically big enough in terms of the forward process can converge to the unique Gaussian. So typically we use the 1000 as kind of the parameters for the t, but you can basically control the number of these kind of steps in your own implementation. And also there are lots of kind of some practical choices for the beta. There are some, so you can also play with like this beta, like what will be kind of the best parameters in terms of like getting some kind of the good quality of the outputs. So there are some multiple options. Like in one paper, people basically linearly interpolated the beta from the 10 to the minus 4 to the 0.02. And there are also some kind of the cases like making this kind of the parameterization the beta to be slightly more complicated with the cosine function and some kind of the parameters here. So you can choose any kind of the parameters that you want to choose. And also here, one quick thing is that based on the definitions of the beta here, yeah, we also have some kind of the other parameters, which is basically defined based on the beta, right? The alpha t and the alpha t hat, those are basically some of the new variables that are defined with the beta. So here, one quick question that I'd like to ask is that actually the thing is that since all the beta and beta and the alpha t hat, those are basically connected to each other. Actually, instead of like defining the beta, here, instead of like defining basically the values of the beta here, we can actually define the alpha t, the alpha values, or alpha hat as well, right? So instead of like when we define the set of the beta, if we basically define the set of the alpha hat t here, then can we also calculate the beta with respect to the alpha t hat? So that's like the first question. So let's think about the case that now, from the for the time step from the t, we can consider having the time step from the 1 to the 1000. Yeah, then we're gonna also have the beta t from the beta 1 to the beta 1000, right? But instead of this, like we can consider making the alpha t hat, basically defining the alpha t hat, alpha hat from the 1 to the 1000, right? And based on that, we can basically calculate the beta based on the numbers that we define for the alpha hat, right? Then if we have the set of the alpha hat, from this, how can you compute the beta t for each of the time step t? Yeah, so we can see that basically from the definition that we defined in the this slide, basically, alpha hat was basically defined as kind of the product of the alpha here. Then also the alpha was the 1 minus beta. So from this, actually, we can see that here. So the beta t should be basically 1 minus alpha t hat minus alpha t minus 1, right? So yeah, so that's basically what we can see. So what we can do is that instead of like define the beta, actually we can define the alpha hat, and basically we can calculate other the variables based on those numbers. And in terms of like define the alpha hat, we also need to make sure that the alpha hat should be some kind of the value which is starting from the 1 and basically decreasing over the time t because of the definition of the beta. Right? Actually, that's kind of also the property to make the forward process to converge the unique Gaussian. It is clear. Yeah, and also the good thing of the having the definitions of our default the process was that we can also directly jump from the x0 to the any kind of the arbitrary the xt for the arbitrary the time state t, and also this kind of the jump from the x0 to the xt was also defined with as the Gaussian as well. So we could basically derive that if we have some multiple the stack, basically a stack of kind of the multiple the Gaussian the transitions. That kind of the stack of the Gaussian transition can also be represented as kind of a single the Gaussian the transition. So this was kind of the property that we could see. And then from the university process, basically we were interested in basically defining this. So while we cannot basically directly estimate the parameters for the conditional the probability, the xt minus 1 given the xt. So this is basically the reverse the transition, right? So how we basically get the probability of the xt minus 1 given the xt is basically something that we want to know to run the reverse process. And we also want to model this as kind of the Gaussian the transition, Gaussian the distribution, while we don't know the mean and the covariance. But the thing is that if we basically see this specific the conditional distribution conditioned by the both xt and the x0, then we can easily basically derive that this is also another the Gaussian distribution, where basically we can also calculate the mean and the covariance like this. So we can basically directly calculate the mean and the covariance in this case. And also the thing is that here the mean was defined as kind of the linear interpolation between the xt and the x0, and the covariance is basically defined based on the parameters that we defined. So one more thing here was that basically if we can also, since basically xt can be represented as kind of the this kind of formulation, when the epsilon t here is basically a noise which is samples from the unique Gaussian. So in this case, that where we know that the epsilon t is given. So we know what is basically the noise that basically resulting in the xt from the sample of the x0. So this epsilon information is given. Then from the xt, we can basically reversely calculate the x0 from both the xt and the epsilon dt, and then the mean of this distribution can be now defined as kind of the function of the xt and the epsilon t. So that's basically the thing. So if we want to basically get the information, get some kind of parameters of this specific conditional probability density function, the only information that we need to know is either the pair of the xt or the x0, or either basically the pair of the xt and just the epsilon t, because from the xt, from the epsilon t, now we can compute the x0. Basically, if we know like what's the xt and what's basically the noise that was added to basically produce the xt, and from that we can basically also guess what is the x0 that was basically making the jump from the to the xt. And based on that, basically what we could see is that if we want to basically minimize this loss function, basically maximizing the probability, the values for each of the samples that we are having, then basically minimizing this loss function becomes the same as basically we are basically having the noise predictor, the epsilon t predictor, and then basically minimizing this kind of the L2 loss between the noise that we are predicting for each of the xt at the times the t, and also the real noise that was actually added to basically the xt from the x0 to basically result in the basically the xt. So this was kind of the things. And from this, basically, what we could see is that actually in the training of this kind of the noise predictor, we don't need to basically go in a sequential way. So that's kind of also the key thing. So in the training of the DDPM pipeline, we don't need to go into kind of a sequential way, but we can actually sample any arbitrary time step t in the range. Also from starting from any kind of the data sample that we know. And then we are also sampling the kind of the Gaussian, unique Gaussian the noise, and then we are jumping from the x0 to the arbitrary the xt, and then what we can see is that now we are basically checking whether we can recover the noise that we added from the xt information. So we are basically feeding this xt information with the time step t into our noise predictor, and see whether we can basically predict the noise that we added to basically make the xt from the x0. So this was kind of the loss function that we are basically minimizing over the training of the DDPM pipeline. So also one key thing is that we are basically repeating this process, not in a sequential way, but from any arbitrary sample, the x0, we are also sampling a time step t, and then basically jumping to the time step t with some kind of the sample, the noise, and checking whether basically we can recover some kind of the noise that we added using the noise predictor. It sounds okay. Yeah, so that's basically kind of things that we are going to do. But actually, we're gonna see that the goal of the noise predictor is just not basically recovering the noise that we added. It's more about basically minimizing the expected value. So we can also get into the exact meaning of like what's the things that we are doing in terms of minimizing the noise here. But in the generation process, actually, we need to do some kind of more sequential way. So we are basically starting from some kind of the sample from the unique Gaussian, and starting from there, we are basically running the reverse process from the time capital T to 1. So in this way, what we can do is that for the xt the arbitrary time step t, now we are predicting the noise that we are basically we added to the xt, and then we can basically predict basically the x0 from the xt and the epsilon t. And from that, we can basically predict the mean of the distribution of this, right? Given the xt and the x0, right? Now we are having some kind of the prediction of the x0 here. So based on that, we can now predict the mean of like this distribution. And based on that, we can also get the sample in the time step will be t-1 by also adding some kind of the unique Gaussian noise as well here, right? because basically we are sampling from this distribution by basically predicting the mean of this Gaussian. So that's basically what we are going to do. Any question on this? So basically, these will be basically things that you need to in the assignment 3. So if you started to implement the assignment 3, actually the due of the assignment 3 is this coming Sunday. So you only have the 1 week. So I guess the implementation won't be that difficult, but basically there are 2 tasks. One is basically running the DDPM and DDIM, the models that we also discuss. In the simple case, with some kind of the 2D examples, and you also need to implement the same thing for the image generation as well. So please check out the code and see if you have any kind of the questions or the issues with implementing this. Please let us know. So the due date of the assignment 3 is this Sunday. So you actually see that in the implementation, actually you see that actually the implementation is quite simple. While all the kind of the math might look basically a little bit like the convoluted, you're gonna see that actually the implementation wise, the algorithm is quite simple. And also the training is much easier. So it doesn't like the kind of the GAN, you know, that the GAN training is like way more like the unstable. And you're gonna see that the training of this diffusion model is much more stable than some kind of GAN kind of the pipeline. And also implementation-wise, there are also like multiple some kind of the design choices that we can make, especially for the neural net design. For the image diffusion model, you can also use some any kind of the architecture. But typical, basically the neural network, the architecture that people are using is basically the UNet with some kind of the less than blocks and also the some self-potential layers. And then also we are feeding basically the time t information. So this is basically the noise predictor, right? Taking some kind of the noisy, the perturbed, the noisy the data here, and also the time step as well. So the way that people are adding the time step is basically feeding basically the time t with some kind of the positioning encoding that also we discussed in the previous lectures, and then basically feeding this into the resonant blocks, each of the resonant block like this, with some kind of some normalization technique. So you might also need to check out some of the implementation, the details, to basically do some the assignment 3. Any questions on the assignment 3? So today what we are going to discuss more about the diffusion model is that we're going to briefly see what's the meaning of like this diffusion model, like why people design the diffusion models in this way, and what's kind of the things that are basically related to some kind of the previous diffusion models. And also we're going to briefly discuss some of the ideas, very typical the ideas in terms of like how we can improve the quality and also the speed of the diffusion models. So that's basically what we are going to do. So we're going to first briefly see how this kind of diffusion model is basically connected to the variation of the autoencoder, so VAE. So I'm going to assume that all of you basically have some basically basic idea for the VAE, but just in case that you are not familiar with the VAE, let's also briefly recap the idea of the VAE. So actually the idea of the VAE is kind of the same with the diffusion models, only in the way that we are also going to map the data distribution into some kind of the target distribution. And also basically we are learning the mapping from the prior distribution to the data distribution, basically running this in a way that the final data distribution can be represented in this kind of the single transition form. You can see that this is kind of the same with the diffusion model, but you can see that now this basically only involves basically a single transition from the variables sampled from the prior distribution to the variables that are sampled from the data distribution. So this is kind of the case. So we are basically making some kind of the mapping from the data distribution and the prior distribution in a way that we are only having the single transition step in some kind of reverse process. So that was kind of some beginning of all the idea starting from the VAE. Then here the question is basically, let's see that like this is basically the prior distribution. So we're gonna set this as kind of the unique Gaussian, right? And here also still the question is that how we gonna basically estimate the some of the parameters like this conditional distribution. So that's basically what we are going to do. So basically, how we can do that? If we basically have the information of like this, the conditional distribution, then what we can see is that we can basically calculate the probability for the all the given the data, the samples, basically by calculating this integral, right? So what we can see here is that we can basically have some lots of the some kind of infinitesimal of these samples in the space, and then we are basically multiplying the probability the values for that the samples, and also for the given the prior distribution, and also this conditional distribution as well. And based on these the quantities, now we can, if we can compute the integral, then we can also get the probability values for the each of the data samples that we have access to. But basically, we want to discretize all the things. And the basic idea that we are discretizing this is that we are using basically the Monte Carlo sampling. So instead of like taking the integral, what we can do is that we are basically taking the samples here. So we are basically taking the samples from this. And then we are basically summing up this quantity. And basically taking the expected value for the all the samples that we are sampling from the prior distribution by summing up these values. So this will be basically kind of some discretized version basically computing this integral to basically compute the probability for each of the data samples. So that's basically what we have here. So if we want to basically compute the log of the probability of each of the data sample, then we can take the expected value of this basically this conditional the probability for the given the samples from the unique Gaussian and taking the log of that. From the density inequality, what we can see is that if we basically switch the log here and the expectation here, basically taking the log first and then computing the expectation, then this basically becomes the lower bound of the quantity that we are basically going to be compute. So what we are typically going to do is that we are basically maximizing the lower bound in a way that we can also maximize the probability for the given the data samples. So that's basically the very typical the loss function that people are using. And if we basically want to find the best linear parameters in a way that we can basically maximize this probability for all the samples that we have, then basically we need to compute this expected value, right? So basically what we can see is that if we basically find the best, some model the parameters for this transition, what we need to do is that for all the data samples that we are having here, we are also having lots of the samples that we are sampling from the unique Gaussian, and basically taking the sum of this kind of log the probability. So that's basically the way that we can basically compute the sum of all the probability for the given the samples, right? And basically we want to find the parameters here that can basically maximize this kind of the probability for all the data samples. And this computation will be very expensive in terms of that we're gonna need not only lots of the samples of the X, basically the data samples, but basically to compute the probability, we also need to have the lots of the samples coming from the unique Gaussian as well. So basically, we need to consider basically lots of the pairs coming from the data distribution, and also the lots of the samples coming from the unique Gaussian as well. So all these kind of the multiple these pairs of these X and Z will be needed to basically accurately compute all the probability values, which will be basically very time consuming. So this will be basically the case. So like making some of the challenges in terms like how we basically find the best parameters, because to basically optimize this kind of the equations, we need to have the lots of the samples of both the X and Z. So that's why basically people say that this kind of the optimization is kind of the intractable. So what people want to do here is that actually we want to do some kind of the importance sampling in this kind of the Monte Carlo sampling idea. which is the thing is that if we basically get some kind of information like the probability of the X given the samples from the unique Gaussian, and if we can actually get some kind of the opposite as well, like basically getting the conditional the probability of the sample Z, which is the sample from the unique Gaussian, from the given the data distribution, basically having some kind of the opposite of the conditional the probability. Based on this information, then we can do some kind of the important sampling. So basically multiplying these two here. So the meaning of this is that when you now compute the probability, like on the data sample, the X here, we are not just basically sampling the Z with some kind of the given the prior distribution, but depending on the X that we are basically calculating is the probability, we are basically doing some kind of the sampling, some adaptive sampling based on the X here. In a way that basically the computation will like this becomes like much more efficient. So now what we can see is that we are switching the equation here in a way that now we are not sampling from the prior distribution, but basically the sampling of like this conditional probability function, which is basically kind of the opposite of the probability like that we want to model. So we want to basically model this the X given the Z. But if we also have the information of the Z given the X, then we can basically do the sampling based on this. Then that will basically becomes much more the efficient some kind of the computation in a way that we can reduce lots of the samples of the Z while basically getting some kind of the accurate the probability for the given the X. So this basically sampling becomes like unbiased only when basically this Q Z given the X becomes some kind of the opposite probability the density function of the X given the Z. So this is kind of giving the idea. But here also the problem is that we want to model this P, the probability the X given the Z. So basically this is also the unknown information. And given that when this is the unknown information, how we can get also this information, like probably the Z given the X. So both of them are actually the unknown. So what we are going to do in the VAE is that actually we are jointly training both, the probability of the Z given the X and also the probability of the X given the Z. So you can see that actually the probability of the Z given the X becomes kind of the encoding process. Given the input, the data point to the X, how likely that will be able to map to each of the sample of the prior distribution, the unique Gaussian samples, right? So this way becomes some kind of encoding. And the other way around is basically decoding, right? So given some kind of sample from the unique Gaussian, then how we can basically see how likely this basically maps to one of the data points. So this is basically becoming the decoding the process. So by just tweaking, by leveraging the same the auto-encoding the architecture, basically we are now learning this kind of this way the conditional distribution of the probability of the Z given the X, and also the conditional distribution of the X given the Z in a way that we can do some kind of the importance the sampling in terms of like computing the probability for each of the data sample the X, and then we are basically optimizing all the parameters in a way that the probability for each of the data samples becomes maximized. So that's basically the basic idea of the VAE. So we can basically say that the VAE is kind of like related to the diffusion models in a way that is also the same in terms of mapping the data distribution into the target distribution. But also here, basically, the limitation is that this was basically the case that we are basically mapping the unique Gaussian samples Z into the data samples of the X using the single transition, right? So basically, since we are basically mapping the Z to the X is the single the transition, and also the other way around is also the map as kind of the single transition, right? And we also basically want to model both of them as kind of the Gaussian. And as we can see in the diffusion model case, as we basically have this kind of single transition case, actually it becomes much more difficult to model one of the other way around as kind of the Gaussian as well. So here basically what we want to do is that we want to basically model the Z to the X as kind of the Gaussian. But then the question is that the other way around is also the Gaussian as well. So typically, when the when this is the Gaussian, this does not guarantee that the other way around is also the Gaussian. So the only case that we can basically approximate when this to be basically the Gaussian is the case that we have seen in the diffusion model. When basically the beta in the transition deformulation is basically small enough, then we can consider this to be also close to the Gaussian. But for some other kind of the random cases, actually it's hard to expect that the other way around of the conditional the distribution would be another Gaussian as well. Which means that for such kind of the cases that we are having the single transition both for the encoding and the decoding, basically this and also modeling these two as kind of the Gaussians, it's basically hard to basically get some kind of the very accurate mapping because like we are just using the Gaussians for the single transition cases. Actually, that also results in basically the idea of the hierarchical VAE. In terms of the we are basically also not using the single transition, but we also stacking some multiple transitions in a way that basically we can also use the Gaussians for each of the steps in a way that we can get also the better sort of the mapping from the data distribution to the product distribution and also the other way around as well. So that was kind of some initial idea in terms of like how we're gonna basically use the same deformulation in the VAE while basically improving the quality of kind of the mapping in terms of like stacking some multiple Gaussian transitions. So this is also kind of the similar with the different models, but the way that we are learning the probability density function, the distribution is also basically different. And also this specific hierarchical VAE deformulation is known as that it's really difficult to optimize all the kind of the parameters. So that's why basically we started to see some kind of the idea of the diffusion models and also the score-based models. Is there anyone also who heard about these score-based models? So probably you might be able to see that people are basically interchanging the terms of the diffusion models and the score-based models. So sometimes like people call the diffusion models as kind of the score-based models. And actually what we can see is that these two are basically the same thing, except for some kind of some minor details. And we're gonna basically see how these two things are basically connected to each other. So in the VAE case, and also some other kind of the previous the generative model cases, the goal was basically to directly model the data distribution, right? So this is basically the probability density function in terms of how likely each of the data point is one of the point of the real data, right? So we basically wanted to basically directly model this data distribution. But in this score-based model, actually the goal is that we are not going to directly model the data distribution, but actually we want to model the gradient of the log likelihood for each of the data point. So instead of basically getting the information of the Qx0, we just want to get the information of the gradient of the log the Qx0. So what we are going to see is that even without having this kind of direct the probability density function, only when we have this kind of the gradient of the log of the probability density function from this, still we can do some kind of sampling. So that's basically what we are going to do. So also one thing that you need to know is that typically this gradient of the log likelihood, this function is also called this core function. So this core is basically not this core that you basically think, but basically this core here basically means the gradient of the log likelihood, basically this function. And that's basically why we are basically saying that this is this core-based model. So if we have this core information from this, how we can do some resampling of the original data distribution. That's basically what we are going to do. And the basic idea for this is basically using some kind of some simulation idea in the physics, which is using the Langevin dynamics. So what we can see from the idea of the Langevin dynamics is that So what the Langevin basically says in this kind of the framework is that while when you don't know the exact the likelihood the functions for the data distribution, if you only have the gradient of the log the likelihood, actually you can start from some any kind of the arbitrary some kind of the prior distribution, and you can basically iterate this kind of a procedure in terms of basically you're distributing the samples from the PXDD distribution into this kind of some kind of the dissipation kind of the way. That if you basically iterate this kind some kind of the some diffusion kind of things multiple times, you can see that actually at the end of the day all this kind of the data, the samples will basically will become the samples of the real the QX0 the data distribution. So that's basically the idea of the Langevin the dynamics. So you can also see that here we are only using the information of the some kind of the gradient of the log likelihood, and just starting from some kind of the prior distribution, and just like repeating this process like the multiple times, then you can see that actually at the end of the day, the data samples becomes the or the original the samples of the data distribution. Then you can see that this idea is quite similar with the reverse process that we have been seeing, right? So it's really starting some kind of some prior distribution, and basically dispatching this kind of the samples with some kind of the information that we are having, some kind of the original the data distribution, with some kind of the noise that we also adding here, right? Some kind of the some unique Gaussian noise. And if you basically iterate this process the multiple times, it will basically converge into some kind of the data distribution that we want to learn. But here, while we can still like sample from the original data distribution, the only information that we need is basically this score information. So basically, if we can basically only access this score information, then from this kind of iterative process, we can do some kind of the sampling, the data sampling. So that's basically the basic idea of this score-based models, and you can see that this is really related to the reverse process that we have seen, right? And this is some kind of animation that we are seeing some kind of the diffusion process. You can see that the blue dots are basically samples from some kind of the uniform distribution over the space. And over the time, when you basically move them to the equation that we have seen in the previous slide, you can see that it's basically converging to some kind of the distribution that we basically wanted to see. Yeah, you can see that the red lines are basically indicating the data distribution that we want to learn, and the black arrows are basically showing some kind of the this core information for each of the point where we need to to where we need to send each of the data point. So you can see that these kind of the black arrows are basically this core information. Okay. So yeah, so basically here for this kind of score-based models, the only information that we need is basically this core, right? So if we can also have some kind of this core prediction network for each of the data point in the X, that can basically predict the score the information for any kind of data point. Based on that, we can basically run the Langevin dynamics in terms of this kind of sampling. And the way that we can also basically minimize basically learn this kind of the score-based the score the prediction the network is also basically the optimizing the neural network with this kind of objective function. So basically, minimizing this kind of the expected value, taking the samples from the data distribution, basically, and then calculating the score and then minimizing this difference. But can you see the problem like this model? Especially this objectivity function. So this objectivity function is that we are sampling the data point X from our data distribution, and then basically calculating the score for the sample, and then basically checking whether our score the prediction the network can basically predict the accurate the score at the point that we sampled from the data distribution, right? What are the kind of issue of this? Any idea of this? Actually, if we go back to the previous slide, yeah, so we are starting from some kind of the arbitrary DD points that are sampled from the uniform distribution over the entire 2D space here, and then sending those points into the destination D point, which becomes the sample of the data distribution, while basically having this core information over the entire space, right? So the problem here is that while basically we know we need to basically have the this core information for all the places over the 2D space. Now we are doing some kind of the sampling from the data distribution, right? Which means that so let's say like this is our kind of some data distribution that we want to basically match using the Langevin dynamics. And then we pre-sample the X based on the data distribution we have here. Then we're gonna actually have the lots of the samples near here, right? Also the here, right? So this is kind of the case that like for the some image generation, for example, we're gonna have some kind of the lots of the real images, and those real images would be basically samples from the data distribution. And we're gonna basically train our score prediction network in a way that we can get some kind of the accurate score in these regions, right? But the thing is that actually this was kind of the case that we are starting from the uniform distribution to go into the data distribution, which means that we might also start from any kind of points here, right? Any points in this 2D space. And for all these kind of the arbitrary the position, we also need to have this core information. But our score prediction network might be basically inaccurate for those regions because we basically don't have much of the samples in the red region, right? All the samples that we have are basically some samples from the data distribution, and those might be basically concentrated on these regions, right? So which means that at the very beginning, that when we start from like those regions, the score information that we are getting might be basically inaccurate. So the first few steps in the Langevin dynamics will basically lead to some kind of the wrong positions when sending all the target, so all the sample the points. So that's kind of things. So here the question is that where we need to have the samples, the samples to basically optimize this equation. If we only take the samples, the X from the data distribution, then we may not be able to basically get the accurate score information for the other regions. So actually, this basically might mean that we need to actually have some more samples, not only from the data distribution, but somehow in between the data distribution and the prior distribution, in a way that we can actually get the accurate score the information over some kind of entire space. So that's basically what we are going to do. So for that, what we are doing is that to basically get some kind of the samples from some kind of the intermediate space, actually we are perturbing the data points gradually in a way that now we are not only concentrating on like those samples, but having some kind of the dissipated samples over the entire space. And for those samples, we are now computing this score. So that's basically what we are going to do. So what we are going to do is that we are basically estimating these quality functions, not for the samples from the data distribution, but also we are perturbing all the data points in a way that we are having some more the bullet points over the space, and then now we are getting the score over some kind of the entire space. And so the whole procedure is that now in terms of also getting some kind of the security function, we are also running the Langevin dynamics, kind of like the sequential way. So in a way that we can basically so we are basically having this data distribution here, and perturbing some more data in a way that we're basically having some kind of the noisier data distribution and the noisier data distribution. And then what we do is that we basically run the Langevin dynamics in a kind of the reverse way. So we start from some kind of the uniform the distribution, and we first run the Langevin dynamics to basically get this some kind of some perturbed distribution with the square function like this one, right? This is kind of the one step. And the next step might be is that we also get this slightly less basically perturbed the data distribution by basically running the roundable dynamics with this core that we got from this distribution. And then we are basically repeating this process in a way that we are basically having some kind of the multiple, some kind of the distribution, which becomes some kind of the in-between distribution between our data distribution and the prior distribution in a way that the score prediction can be much kind of like some kind of the accurate for each of the intermediate steps. So basically having some kind of the multiple the intermediate steps in a way that the target the data distribution and the previous the distribution the difference between these two becomes basically minimized in terms of that we can basically see where we need to basically constantly know more in terms of like some kind of the accurate the score information. So that's basically the idea of the basically the annealed the roundable the dynamics. And you can see that actually the idea that we are basically gradually perturbing all the data points while basically controlling the scale of the noise here is actually exactly the same we default the diffusion process. And also the kind of the same thing is that we don't need to basically add all the noise in the kind of sequential way. We can actually, basically add some kind of the more perturbation in a sequential way, but basically adding all the kind of the perturbation in a sequential way is basically the same as kind of like we are basically adding some kind of the bigger noise at once from the data distribution to some kind of the time step t. So that's basically also the same with that. We can also directly jump in the forward process in the DDPM, the diffusion model kind of the framework. So you can actually see that these two are exactly the same thing. And also, if we basically make some kind of the time step to be really going into the infinity, having some kind of the infinite number of the time steps, then this also becomes the case that we are running all this kind of the process into the continuous time domain. And then we are not going to get into all the details here, but we're going to see that this basically the process is actually the same as kind of like learning this kind of the stochastic differential equation. So you can actually model all this process in a kind of the continuous domain, having this kind of equation. And this becomes basically the forward process that we are basically gradually adding some kind of the noise here. You can also see that once we basically have this kind of the forward process, the other way around, basically running the roundable, the annual the roundable the dynamics is also basically represented as this kind of the stochastic the differential equation. And also like some kind of the details here is that the DDPM the model that we have seen is kind of some kind of the discretization of this specific the SDE deformulation. So in this way, basically these two, the score-based models and also the diffusion model that we have seen are basically exactly the same thing with some kind of some minor details in the formulation. So the important thing that we need to see is that, the idea of this score-based model is to get the score information, right? So once we can get this score information for every time step t, so what we are doing is that for every time step t, we are basically running this the roundable dynamics with this score the information in a way that we can basically map the data distribution with some kind of the p time t into the p t minus 1, right? Which is some kind of the roundable dynamics. So the only thing we need to do is basically the score information for each of the time step t. Then what would be basically the score information in the DDPM model? So if we basically go back to the DDPM model, what's basically the score information that we want to basically get? So if we basically derive all the things, what we can see at the end of the day is that actually we can see that if we basically derive all the things here is that we can see that the noise that we are predicting using the noise predictor is basically giving this core information. So that's basically kind of things. So what we are actually getting with some kind of the noise predictor is basically some kind of the expected value for the all the epsilon t coming from the pairs of the xt and the x0. And basically, if we basically get this kind of expected value, that becomes some kind of the scaled the noise, the score information that can be basically used in the roundabout the dynamics. Actually, we can see that the reverse process is kind of the sort of the reformulation of the roundabout dynamics in terms of we are dissipating all the samples in the previous time step using the score information using basically which is predicted using some the noise predictor. So that's basically what we are doing in the different models. So that's kind of the explanation in terms of what we are doing with the diffusion models. So this was not just like getting the epsilon information from the pair of the xt and the x0 and just like checking whether the network can recover this information, but actually we are getting some kind of predicting the expected value of this epsilon for each of the intermediate for any kind of the data point in the intermediate time step in a way that this expected value becomes this called the function in a way that we can just run the roundabout dynamics that we can get some kind of the data samples. So that's kind of some kind of the fundamental idea behind the DDPM model in terms of like why we need to basically get this information. So this information was actually related to this core information that we just need for the sampling the process. Any questions on this? So yeah, you can basically check out some more the details in the slide later. But I guess we also need to move on to some kind of the next part. So yeah, so those are kind of the basic idea in terms of why we need to get all the noise information and what's the exact meaning in terms of how we can get the data samples from the noise information that we have. And actually, let's see some kind of the practical issues as the different models as well. So the good thing of the diffusion models is that actually we could see some kind of the generate models like the GAN here and the VAE and also the diffusion model. And the good thing of the GAN is that it can basically produce the high quality samples, and also the sampling process is quite fast. But we know that the GAN can basically be very unstable in terms of that it can have the multi-collapse problems and basically losing some kind of the diversity in the sample points. And the good thing of the VAE is that basically it can basically be very fast in terms of the sampling, and it also does not have this kind of the multi-collapse issues. But typically the quality of the sample is basically much worse because as we have seen in the previous slides, the transition for both the forward and the reverse processes cannot be some kind of the accurate mapping between these two kind of the distributions. So that's why basically people came up with this idea of the different models, which basically allows to basically have some high quality samples and also not having any kind of the multi-collapse issues, basically having the diversity. But the problem of the different model is that basically both the training and also the generation is really slow because we are having some kind of the iterative steps. So what we can see is that in the practice, so this was basically the first paper which was actually published in the last year or 2021. But this was basically the first work that started to basically beat the quality of the GANs. So that's why basically different models became quite famous in terms of that. This became some kind of the state-of-the-art technique in terms of like generating all the high quality samples, especially the image generation. But what we also could see is that actually it takes huge amount of the time. So what we actually could see for this specific model is that actually for the training it takes about like more than 100 or sometimes like even 1,000 days, not hours. Just train a single this kind of different models using a single V100 GPU. It actually takes like some years if you are only using a single GPU. So that's why you need to also have lots of GPUs. And even for the generation, to basically generate some kind of the 50,000 samples, it also takes like 5 days using the A100 GPUs. So the competition is like way slower to be compared to some previous the generated models. So people also discuss lots of the ideas in terms of like how we can reduce the computation time in a way that we can also make this diffusion model to be a bit faster. So one simple idea, some kind of the engineering the idea for that is the latent diffusion model. So this is kind of the became some kind of the standard way to make some kind of the especially image generated models. In terms of the idea is kind of simple, which is basically first reducing the dimension of the data in a way that all the computation, like basically especially the noise prediction, becomes like the network architecture becomes some kind of the more compact in terms of like dealing with some kind of the small dimension of the data. So the idea is basically very straightforward in terms of like we are first having the autoencoder and using the autoencoder as some kind of the dimension reduction kind of the technique in terms of that. Like for example, if we are having the 256 by 256 times 3, this kind of channel, then we are basically mapping this into some low dimension space. For example, like 64 by 64 by 4. Or even like 32 by 32 by 4 or something. So basically, we are reducing, doing some kind of the downscaling of all the images. But when you do some kind of downsampling of the images, it doesn't need to be really basically just like decreasing the resolution of the images, but we are basically encoding all this kind of the information in the images into some kind of the latent images. So this is not the real images, but some kind of the latent images that basically encode all the information in the color images that can be also decoded into the original the image using some the autoencoder. So the idea here is that we are basically first decreasing the resolution, basically the dimension of the data, and then running some kind of the noise prediction, the architectures in a kind of the compact, the more compact data space. So people also experimented with all the downsampling in the cases. So as I said, like here the downsampling is just not just like decreasing the resolution of the images, but actually mapping the images into some kind of the more like lower the resolution of the latent images. And here the F basically means like the downsampling the factor. So basically when the F is the 1, which means that there is no the dimension reduction. So the original images was basically used as kind of input, and here the LDM when the F is the 4, which means that the resolution has been basically decreased by the factor before. So if you start from the 256, it was decreased into the 64. So that's kind of this. So as you can see, as this like the number of the F is basically increasing, this means that we are also compressing the data much with some kind of the more like smaller the dimension of this space. And here the question is that what would be kind of the sweet spot in terms of like choosing the downsampling the factors. So practically, what we can see is that if there is no compression, then it will also take some lots of the time in the training because of the data size is too big, right? So this is like one extreme case, and the other extreme case is that if we compress the data too much with some too much kind of downsampling the factors, then also the compression itself is basically losing too much information. So then there's no way that we can basically produce some kind of the high quality the outputs. So basically there will be some kind of a sweet spot in terms of like while we are not losing that much information in the autoencoding the process, how we can basically also reduce the training time. So that's kind of the things. And the typical solution for this is that if you basically choose like the downsampling factor of 4 or something, then you can typically get some kind of the good results in the trade-off in terms of like not losing that much information in the autoencoding and also making the training time much faster, like twice or the third times the faster than typical kind of some of the different models. So this LDM is kind of the very standard way to train the different models. So if you see some kind of some kind of famous, some public, the pre-trained diffusion models, pre-trained with some kind of the large scale, the image, the data set, like the stable diffusion is also the most famous, the pre-trained model. For those kind of diffusion models, you can see that actually they are using the LDM, the idea. using first like mapping all the things into the latent space and learning the diffusion models in the latent space. But this is kind of some sort of the engineering idea in terms of like we are reducing some kind of computation time by some sort of the dependency reduction. But also here the question is that in the forward and the reverse process, one of the reasons that we are having some kind of the long computation time is that because we are having some lots of the iterations, right? And also we discussed that as the T is increasing, then also the forward process is better converting to the unique the Gaussian distribution. So typically we are using the T to be the 1000. So it can be longer. But also here the question is that can he also reduce this number of the iterations of the T while not sacrificing the quality of the samples? So actually that's kind of the more the fundamental question, right? So how can you basically reduce the number of the iteration, the steps, while not basically compromising the quality of the data samples that much? So that's basically also what we want to do. So that's basically the point where basically we also start to see the idea of the DDIM. So we're gonna briefly get into this idea. Before this, do you have any questions? Yeah, so let's briefly see the DDIM, and also in your assignment 3, you also need to implement both the DDPM and also the DDIM. So actually the idea of the DDIM might be a little bit complicated, but let's get into some of the ideas here. So the basic idea of the DDIM is that actually we have seen the very specific the forward and the reverse process, right? And that was basically the case that we are modeling both the forward and the reverse processes as kind of the marker of the chain, right? The xt only depends on the xt minus 1. Having this kind of some sequential process in terms of like how we map the x0 to the x capital T and also the other way around. And here in the DDIM, the framework, actually we're gonna see slightly different the forward and the reverse processes. But here the thing is that now we are changing the forward and also the reverse processes, but not making some big changes, but making some small changes. So actually one kind of the big change in the forward process is that we are introducing some new parameters, the sigma here. So actually we have seen the previous this slide, we had the parameters of the beta T, right? Which can be computed if we have the set of the alpha head. So that's what we have seen in the previous slide. We're going to assume that now we have the parameters of the alpha head and also the sigma as well. So this is basically the new parameters. And the forward process is now defined in this way. So we need basically compute some kind of the conditional the probability of the xt from the x0. So we are not going into this sequential way from the x0 to the x1, x1 to the x2. So this was basically the way that we are defining the forward process, right? And now we are going to switch the forward process in a way that not going in this way. So we are not going from the x0 to the xt like in this way. Actually, we are going into this the other way around, which is basically jumping from the x0 to the x capital T and coming back from the x capital T going down to the xt. So now this is the way that we are going to define the forward process. So still what we can see is that we can do this kind of the jump from the xg to the any kind of the xt, and this jump, this transition is defined in the same way with the DDPM, right? And now we are also modeling this. Given the x0 and the xt, now we are modeling this specific conditional the distribution of the xt minus 1 given the xt and the xz into this specific way. So in the DDPM process, we actually derive this basically the conditional distribution from the single transition and also this full jump. And now the thing is that we are not defining the single transition. Actually, we are now defining this and this. So the difference between the DDPM and the DDIM is that if I go back to the next slide here. In the DDPM case, we had the qx t from the xt minus 1. This was the basic single transition, right? And also the forward jump. These two. So we could basically, we only define this probability of xt of the given the xt minus 1. And from this, we could derive the probability of the forward jump from the xt from the x0. And based on that, we could actually derive the xt, given the xt, so minus 1 and the x0. So the point was that in the DDPM, from the single transition, these two were basically derived, right? And now in the DDIM, we are now defining qxt. We are now defining this. And from this, now we are deriving qxt, xt minus 1, x0. So the other way around, right? So in the DDPM case, we define the single transition, and from this we define the this forward jump and also this conditional distribution. In the DDIM case, now we are defining this and this, and then based on that, we are defining the forward the transition as kind of the non-Markov way, so which is not only conditioned by the xt minus 1, but now it is also conditioned by the x0 as well. And this can be also derived based on the base rule, using the same base rule that we have seen in this case. So you need to see that the some details here. So the way that we are defining the forward process is different between DDPM and the DDIM. So in the DDPM case, we define single transition, and based on that, the conditional distributions are basically defined. In the DDIM case, we are defining this distribution in a way that we can define the single transition as kind of the non-Markov kind of the process. So that's kind of the difference. And also in a way that when you define the this conditional distribution conditioned by both the xt and the x0, we are also introducing using some kind of the new variables here, the sigma here, which we're going to basically play with in the next slide. So this is basically non-Markovian the process because the xt now depends both on the xt minus 1 and also the x0 as well. So that's kind of the changes that we are making in the forward process. The thing is that, yeah, and also this is the same thing. And this is basically the same. So we are also having this forward jump, which is basically defined like this, using the same alpha hat that we are having in the DDPM case. So these are exactly the same with the DDPM. So now the xt can be also represented as the x0 and the epsilon dt, which is the unique Gaussian denoise. So this is exactly the same with DDPM. So while we are changing the forward process, we are going to make all the rest of the parts to be exactly the same with DDPM. So that's kind of key thing. So now the reverse process is still defined as some kind of the Markov chain like this. And then here also the goal is to basically get the best the estimation of the parameters, the Gaussian parameters for this reverse transition. And also the loss function is still the minimizing the difference between the this single reverse transition with this condition of the probability of the xt minus 1 given the xt and the x0. But here the thing is that while we are also minimizing these two, in the forward process, we defined this conditional distribution in a kind of new way, right? So now this distribution is not exactly the same with the DDPM distribution, right? So now what we are going to do is that we want to basically match this reverse transition to be the same with the new distribution like this. So that's kind of the difference. But also the interesting thing is that while basically we are defining the new the distribution like this one, still the way that we are basically minimizing the loss is also exactly the same. So what we still need to do is minimize that loss function is that basically we are defining this kind of the noise predictor, the epsilon d network, and then also we are minimizing the expected value of the difference between the epsilon t and also the predicted noise here. So here the key thing is that while we are changing the forward and the reverse the processes to run this kind of different process, actually the objective function remains basically exactly the same. So whether you basically run the forward and the reverse processes in a DDPM way or DDIM way, the only thing that you need to do is basically training the noise predictor in the same way. Then you can, using the same noise predictor trained with some kind of the same objective function, you can run either the reverse process of the DDPM or the reverse process of the DDIM. So actually, that's some kind of the way that how people design the DDIM. So that's basically intentionally kind of things that people did in terms of why we are making some changes in the forward and reverse processes. We are defining, modeling these processes in a way that the noise predictor we trained for the DDPM models can be directly used for the DDIM processes. So that's basically very important first. So also the thing is that even when when you basically choose any arbitrary denominative values for the sigma t here, the parameters, still the same noise predictor can be used for the forward and reverse processes of the DDIM. And in the generation D process, it's actually exactly the same, but the only part that we are making the changes is here in terms of how we can exactly compute the xt minus 1. Because this distribution has been changed, right? So we are changing this distribution into the new formulation. So basically, that's why we are making some changes in terms of how we calculate xt minus 1. But the rest of the process in the generation is exactly the same with DDPM. Starting from the x capital T, basically predicting the noise and basically getting some prediction of the x0 here, and then sampling the z here, and based on that, we are calculating xt minus 1, which is basically defined based on the new definition of like this conditional distribution. So that's kind of interesting. While we're making some the changes in the reverse process, we are still using the same noise predictor that was trained for the DDPM process. And then here the question might be that then what's the advantage of like having the new processes? Why do we need to have the forward and the reverse processes? So we're gonna briefly see the differences between the DDPM and the DDIM models. Here the key thing is that basically the way that how we define this conditional distribution, right? So this was basically the things that we derived from the definitions of the forward transition. And this was the things that we directly modeled in the DDIM process with the new parameters here. So here one quick question is that one quick question is that so we are having the new parameters here. And then also in the DDIM process, we can choose this sigma term as we want. One quick question is that can you also somehow make this DDIM process to be exactly the same by just choosing some right numbers for this sigma here? So this is kind of quiz. So we have seen that actually the conditional distribution like these two things are basically different in the DDPM and the DDIM case, right? But if you basically carefully choose the sigma value here, then actually we can make this DDIM process to be exactly the same with the DDPM process. What would be such kind of value of the sigma? Actually, the sigma is squared, which basically makes the DDIM process to be the same with the DDPM process. So since we are running out of time, you can check this out later. But basically, what we can do is that if you see that this was the sigma here. Yeah, my pen is not working now. So somehow we have the covariance of like the term here, which is defined as sigma is squared, and we also have this covariance term here. So if we basically match these two, then you can see that actually these two becomes exactly the same. So if you define the sigma squared like this, you can see that actually these two becomes exactly the same. So basically, this means that we can see that DDIM is kind of the generalized version of the DDPM. So depending on like which sigma that we choose, actually we can make the DDIM to be exactly the same with the DDPM. Then the thing is that while we define the forward process can be some kind of the non-Markovian chain. If we basically match the sigma to be like this, then we can see that actually this becomes also DDIM becomes the Markovian process. But we are basically seeing some kind of some generalized version of the DDPM in terms of that now we can control the sigma value here. And why we want to control the sigma value here. So here one thing is that if we basically make this sigma value to be 0, then what does that mean? So if we go back to the generation process, so in the generation process, what's the meaning of that? We are making the sigma to be 0. So if we are making the sigma to be 0 here, then there's no kind of the stochastic here. So we don't need to sample Z here because like the xt minus 1 will be determined based on the xt information that we have. And also the noise which is predicted by using the neural network. So here basically, once we basically make this sigma to be 0, then the whole process becomes deterministic. If you basically sample the x capital T, then from the same x capital T, you always go to the same x0 because there's basically no randomness, right? This is predicted, computed. We are not going to sample this. Then everything becomes deterministic, right? Then from the same x capital T, you always go to the same x0. So that's kind of thing. So basically, as you make these sigma to be this new parameter sigma to be the 0, then we are basically making all the deterministic process. So that's the basic idea of the DDIM. Then you're gonna see that why do we need to care about like having a deterministic process when you want to basically boost up all the generation process. So we're gonna see the link of like why we are basically having the deterministic process and how does it can basically affect the speed of the generation. And then we're gonna also see some more the techniques that can improve the diffusion processes. And we're gonna also move on to some kind of the ideas in terms of like how we can use this kind of digital models for some kind of the editing the processes, like some image editing or the image in painting. And also we are going back to, we're gonna go back to some original the idea in terms of like how we can utilize this kind of some diffusion models, especially trained to basically generate some images to actually generate some 3D models as well. So we can also move on to the 3D generation next time. So let's continue discussing those ideas on the Wednesday. Do you have any questions? So if you have any questions, please also post on the questions channel in the Slack so that we can also continue discussing those ideas. And yeah, please let me know if you have any questions. This might be also important things to basically do your assignment 3. So let me know if you have any questions. Okay, then I will see you on Wednesday.